Okay. Last time we have introduced the 5-point stencil as the most simple stencil to discretize the most simple elliptic PDE, namely the Poisson equation with Dirichlet boundary conditions. And today we want to start to analyze what we did. So now we have sort of a feeling how to do it, but we have no idea what is it good for. To fix our notation a little bit, I want to point out one thing which I have forgot last time, that is the notion of grid functions. So I said already, or we have seen this already, that one of the specific things of finite difference schemes is that we have the grid points, and that is where, so to speak, everything lives. The domain in between is more or less non-existing for the method, which is also one of the drawbacks of the whole approach. So if we have values at this set of grids, then this defines a function, of course. It's just a mapping. We have a grid point and we have a value at the grid point, but it's difficult to speak in a reasonable sense of properties of this function. So we have no continuity in a reasonable sense, no differentiability, and so on. This is what a grid function is. It's just a mapping from the set of grid points to the reals. Either the grid points or the grid, the closure of the grid is either omega n, omega or omega bar, or the boundary, depending on what you would like to have. On the other hand, of course, we have the representation of a grid function by a vector. But for getting a representation, we have to choose a numbering. We discussed different numberings already yesterday, last time, and we have the impression that the choice of the numbering should not have too much influence on the method itself, on its properties. It has influence on the structure of the matrix which comes out, which may be of advantage for the methods chosen to solve it or not. So we distinguish a little bit between the grid function UH, which is written non-bold, and the corresponding vector UH, which is then written bold, which comes out after selecting an ordering. And the same applies for the data. So here, for example, we've chosen the ordering, and therefore we have in bold print we have a UH. And the same applies for the data which go in. So there are the given continuous functions, the f for the right-hand side, the g for the boundary conditions. We have the evaluation at the grid points, that gives us grid functions, and then we have vectors representing the grid functions. So this would then lead here, in this representation, we get the bold f as the vector representation of the grid function fh, and the g as the vector representation of the corresponding grid function. So also I've omitted here the h, not to overdo the notation. It's something which always depends on the h, because with every new h we have a new grid and we have a new evaluation of these functions. And also we are only dealing here in finite dimensional spaces, so we have a finite m1 as the number of grid points in the interior, where our unknowns, that's the number of our unknowns, and a finite number of n2, the amount of Dirichlet boundary conditions. These are not in the process of convergence we are now going to look at. And in the process, what happens if h goes to 0? These are not fixed numbers. They go to infinity if h goes to 0. And that is the whole thing we have to deal with. So we're not dealing with one specific finite dimensional problem. We are dealing with a whole family of finite dimensional problems for all h's greater than 0, or in a certain range, in any case going to 0. Okay, so this is we have all discussed. And now let's see what kind of questions we want to ask. At the end of the day, what we want to have is we want to have convergence. And as our method only produces values at the grid points, grid functions, the only thing which we can naturally do is to compare the solution which hopefully exists, which of course we in general we do not know explicitly, That's the reason why we do numerics. We can compare the solution with a computed grid function and say something about whether this is a good approximation or not. So we produce a grid function, capital U, out of the exact solution small u, and this again gives then rise to a vector representation which is in a small bold u. So what we want to do is we want to compare these quantities. These quantities are grid functions or equivalently vectors. So we need norms to measure their size. And you hopefully all know that in a finite dimensional space, all norms are equivalent. So we could basically, from this point of view, we could say, okay, it doesn't matter which kind of norm we are taking. But there's a slight thing to be taking into account, namely what did I just say? Why is this argument not correct, what I just did? Why it's not enough to say, okay, everything is finite dimensional, it doesn't matter which norms we are looking at. What did I just say? I just said every problem is finite dimensional, but of course, but this dimension is not fixed. For h going to 0, the dimension goes to infinity. That's what we want to have. We want to approximate the continuous problem by those discrete problems, and of course we want also to quantify this approximation. So we'll see that for every fixed h, of course, all norms are equivalent. So we could take a maximum norm or a Euclidean norm or whatsoever. But if we compare those norms and see how they compare independently of h, there are differences. And they then inherit the properties of the underlying continuous norms. And I hope you know that, for example, in the space of continuous functions, the maximum norm is a stronger norm than the L2 norm, than the norm of the integral over the square of the deviation and the square root out of that. In the sense, if you have convergence in the L2 sense, uniform convergence as is then called for functions, then you can conclude you also have convergence in L2, but not vice versa. And this not vice versa we will also see then here in the discretizations. Okay, so let's have a look at possible norms. So these norms are, so to speak, inherited from the continuous norms. There are two very important ones. The one is the maximum norm, so to speak, coming from the maximum norm, evaluated at the grid points. So we just take the maximal deviation going over all grid points. And the other one is what is called the discrete L2 norm. If you forget about this factor h, what you see here is just the Euclidean norm. You take the vector, you take the square of the deviation, you sum up. We now have this natural double index here in this two-dimensional example, and then we take the square root. But now we have, additionally, we have the h in front of that. Why is this? If the h would be a fixed number, it would be just a scaling of the norm, a 5 or whatsoever. But why is this reasonable and necessary to have here the h in front, if I would call this the discrete L2 norm? Think of those functions. Of course, there's also the question, can I make some functions out of the grid functions? Let's think of a grid function living on this rectangular here. And so at all these grid points we have values. Let's say we have 0 Dirichlet values, so I don't care about them. And what I now do, I make a small box around here and define the function here constant equal to uij here in this box. This is a piecewise constant function what I define. It may be 0 outside here, doesn't matter. well, doesn't matter, 0 outside. So the one-dimensional picture is, we have our grid points, we have some grid values here, and now we take those values for those boxes. Not a very nice function, but it's a function in any case. If I now do this for all the functions involved here, and now do the L2 norm, what comes out? You have to be able to compute the integral over a constant, which I would hope that you can. What comes out for this function here? What comes out if I take the L2 norm of u squared? And this here is h here. It's not depicted like that, it's here a little bit non-equidistant, but let's assume that is all h here. In the one-dimensional picture, 2 dimensions the same thing. What is now this quantity? Oh, let's do it.
Sigma ux into h whole square.
So the sum over the ui and then h, yes.
Whole square then.
As the square, both, or what? What shall I say? Both?
Square. Then root.
Okay. And now you see, that's exactly this thing here. Not really, because now we have to be but we have to be we should reconsider this here. I'm not satisfied with this term here. This is not correct here.
It should be out of
the h should be out of. So, this is the value of the function, and what is the length of the integral of the interval? Is h. So in this case, in the one-dimensional case, we would get square root of h times, let me write it in this form, the Euclidean norm of the nodal values. But in the two-dimensional case, we get 2 h's. We get an h squared for the size of this small patch here. And therefore, in the two-dimensional case, we get an h in front, and in the three-dimensional, then correspondingly. Okay. So, and what we now see, this is comparable to the results you might know for the continuous function, that we now have an estimate of this type. You can try to prove that, it's not very difficult. You can estimate this, what we called, given this, let's go back to fix the notation here, infinity is clear, that is what you're used to. And for some reasons which will come later on, I will call the L2 norm not with an index 2, but with an index 0. There will be reasons which become clearer later on. And because everything is grid function dependent, everything becomes an h. So this is not a fixed norm, that's a norm which changes from h to h. Okay, so what we can do is we can estimate this, say, this discrete L2 norm by a factor, which in this case of the two-dimensional situation is just the square of AB times the L infinity norm. That's quite a simple estimate. And this shows that, in fact, as I said, and as it's the case in the continuous situation, the L infinity norm, the maximum norm, is a stronger norm. If I have convergence in this norm, I also have convergence in this norm, but not vice versa. There's no estimate which goes in the other direction with a constant which is h independent. Of course, we have an estimate saying, so what is possible? I'm not sure about the parameters now, but of course, because they are finite dimensional spaces, we can estimate the with 1 over 2. the infinity norm by a constant times the discrete L2 norm. But this constant now is age dependent. We can this do for every age. And the point is this goes to infinity for h to 0. Can we try to work this out, this constant? I think you have once done this. If you have fixed an Rn, you can relate all the norms you can think of. You have probably done this relating the 2 norm, the 1 norm, the infinity norm. You get certain constants. These constants depend on n, but n is nothing but here related in basically 1 over h squared. N is the number of grid points, and the number of grid points is basically 1 over h squared. Okay, so we have to be a little bit careful with the choice of the norms, and it makes a real difference which norms we choose. And from this discussion, we would say, of course, we would like to prove something about the infinity norm, because that's a strong norm. It really says something about each grid point, or maybe we can only prove something about the discrete L2 norm. And what do we want to have? In the end of the day, we want to have that the method converges, that we can guarantee that this quantity, the exact solution, minus the solution we have computed, in this chosen h norm, converges to 0 for h to 0. That's just a qualitative statement. It doesn't say how this goes, but it gives us a sort of assurement that if we choose our h small enough, if we make our discrete problem large enough, if we put enough effort into what we are doing, we can expect that we are sort of close to approximating the solution of the continuous problem, which is our real aim. The discrete problem is only an intermediate mean to approximate the thing we would really have, and the thing we want really have is the solution of the continuous problem. So this is very qualitatively, so sometimes one can only prove things like that, but what we really aim at is orders of convergence estimates. That means we want to estimate this deviation in the norm by a constant times the power of h. And this power p, which is the order of convergence, this should be as large as possible. So most of the cases we are looking at, we will be concerned with p equals to 1 and p equals to 2. P equals to 1 means I have a sort of a quantitative guarantee which kind of improvement I get when I improve my effort. I halven my h. What does that mean? I double my nodes in the one direction, in the other direction. That means I quadruple my dimension of my problem in the two-dimensional case. And I am sure that that is what this estimate tells me, independent about the constant c, which I in principle do not know explicitly, that I halven the error. Of course, there you see there's maybe a little bit of a drawback with the c is really an astronomical number, which sometimes cannot be guaranteed that it not is. Then you need very, very small h's that this second term is really the term you see in the estimate. So it might well be in bad cases that you are computing in an h range where you do not yet see this order of convergence appear. But let's assume that our constant c are moderate sized constants. So if in opposite to that we have, say, h squared, then with the same increase in effort, we do not have a halvening of the error. We have the error is divided by 4. And therefore, of course, the higher the order is, the better the method. Okay, now how do we get something like that? And okay, we will develop now these notions which we need, and let's have a look what we have. if we now do the following, we take now the exact solution as a grid function, this is this capital U bold, and plug it into the discrete problem. Then the exact solution does not fulfill the discrete problems because we have this change from the differential quotients to the difference quotients. It only fulfills this discrete problem up to a term which exactly reflects the approximation we have done with the difference quotients compared to the differential quotient. So we get here a term with our difference quotient we have chosen, as we have seen last time, of the type h squared times a function capital R, which is depending on everything but can be estimated independently of h, as we have seen, as long as the solution is smooth enough. Okay, now we compare what we have. This this QH is the right-hand side of the discrete problem, so it's just the AHUH. Plugging this in, bringing it to one side, we see the quantity we are interested in. The deviation between UH and capital U is appearing here, but it's appearing as the solution of a linear set of equations with a right-hand side which is small, which has the h square here. So we know we have here a solution of a linear set of equations, and the right-hand side behaves like a constant times, if we now take, for example, the infinity norm, and here if I take vector norms, then I only take one bar to distinguish this a little bit. We have a constant coming here from the infinity norm of the R times the h squared. The question is, can we conclude, this is a very good property, we will give this a name, that is the consistency of the method. That means what we have done in the process from going to the continuous to the discrete problems, this has really something to do with the continuous problem, in the sense that it's getting better and better the smaller the h becomes. The question is now, is this enough? Can we conclude from having an estimate like this that also the, say, infinity norm or any other norm of UH minus U also behaves like C times H squared? What do you think? Is this enough, or do we still need something?
It might depend on A.
What may depend on H?
If A is not good, then it doesn't, UH minus U might not be.
Why? Why? I just have to solve a set of equations, and my error is in a certain, or right in the right-hand side is in a certain size, then also my error in the solution will be of this size. Isn't it so? Is this so, or is it not so? You think this is okay? How is this with the linear equations? We discussed already last time, or last week at least, that the set of equations might act differently towards errors. If I have this set of equation and I make an error, here now not in the right hand side, but even in the matrix, by changing here a little bit, then I see my solution, the intersection of the two straight lines also changes a little bit. Now I change my problem and I take this here. Also a nice two-dimensional problem. And I do the same perturbation. And you have seen already last time, it's a bad drawing now, you have seen already last time that now the error becomes much larger. Okay, if I would have only one problem, then I would say, okay, I have to live with that. There's a certain amplification factor going on here in the problem. That is what is called badly conditioned. I hope you've heard this notion already in numerics. And badly conditioned means one loses a certain amount of significant digits. Of course, it becomes troublesome if we lose, say, 14 significant digits, then it becomes difficult to compute something reasonable, but in principle, one can do something. But what is the difference to our situation now with the h going to 0? And the difference is I cannot draw it like, the first thing is, first of all, the dimension of the problem becomes bigger and bigger. So I have 2, 3, 4, 5, 6, that's not the case, but I have increasing amount of degrees of freedom of equations. That is something which I cannot draw here. So I stick to 2. But what can happen, even sticking to 2, that is my first problem, this is my second problem, this is my third problem, this is my fourth problem. You understand what might happen. In this process of h going to 0, we might see an amplification, an explosion factor, which destroys this small h squared term we have as an error, as an input error in this equation. So we need something more. And okay. First, for coming to this, so this reminds us, this is exactly what we have proven here, and we have found out with computing the approximation we do with the difference quotients. We found out that this constant can be chosen like that. So we need a pretty regular function, C4, that's a big drawback here, but let's say, okay, that is the case. And then we call this the consistent, we will formulate it in a second general, we call a method then consistent, and we will call this, if we call a method consistent if this term goes to 0, and if it even goes to 0 with a certain power of h, we call it consistent to the order 2 in this case. But let's first formulate this notion of consistency correctly. So what is the situation? So we have the set of linear equation which corresponds to the approximation we are looking at the grid points omega h with the discretization parameter h. Capital U is the vector representation of the grid function of the exact solution. And then we have the solution small u of the exact solution small u. Then we have chosen a norm at the grid function, and the same thing of only one bar is the corresponding vector norm if I do not take the grid function but a vector representation. So then I have the set of equations which represent my method. AHU equals QH. In this set of equations I plug in my exact solution as we did it, and if I then see that this error converges to 0, I call the method consistent. And if I even know more, namely that this consistency error which I have here not only converges to 0, but to 0 with a certain power of h, I say I have a consistency order of p in this case. So let's see what we can do with that. So what we can do, the point is what we want to estimate is this quantity. This is now independent of the infinity norm, that's for any grid norm. We want to estimate UH minus capital U. And of course we can write that. Maybe I write this here again. So what we have, UH minus capital U. And of course I can write this with the corresponding matrix of the set of equations, assuming that this matrix is non-singular. As we have seen, I can put this in and take it out, so I have something like that. I can write it in this form. Now, on the corresponding to the vector norms I have here for the tuples, I have, say, an induced matrix norm here, or I can just take a matrix norm which is compatible with a vector norm. So if I have the infinity norm, what would be the induced norm then? What is the induced norm of the infinity norm?
It's the same as
The matrix norm which is induced and which fulfills this compatibility condition here. So I have an induced norm. I have a vector space. I have a vector space. I have a norm in Rn, let's say. And then I have a norm for matrices induced, and I have several forms to do that. What I can, for example, do is look at the supremum of all the norms of the images for the unit circle or something like that. And if I do that, then the norms are compatible, verträglich auf Deutsch, in the sense that I can estimate now the vector norm of Ax by the matrix norm of A times the vector norm of X. And but there might be other matrix norms which also fulfill this compatibility condition. So my question was, if I take here the infinity norm in Rn, what is this here in Rnn? How is this norm called? Ja?
Row-Sum-Norm?
Richtig, Zeilensummennorm. Das ist die Zeilensummennorm und das ist tatsächlich richtig übersetzt. It's a row-sum norm. And you know this for the other ones, you know the spectral norm comes up with a Euclidean norm and so on. So what we need here, we need a compatibility, and we can do this by just taking the induced norms. So we can estimate this term here in the norm by taking the matrix norm of this thing times the vector norm of this thing. That is what we have here. Here we have our nice consistency error, and here we have now a factor depending on h, which in principle can explode. So we need conditions which prevent this factor from exploding, and that is the more, so to speak, the important thing of verifying a scheme. To see the consistency of a scheme is just craftsmanship. You do Taylor's expansion and you see it. There's nothing complicated about that. The big mistake is to say, okay, now I have a nice scheme. Okay, so what we need is, and that is called stability, what we need to have is that in this norm we have chosen here for the matrices. Okay, of course, again, h dependent, let's say the induced norm can be in any other compatible norm. We have to have that those norms, that those quantities have to be estimated. Of course, this is for every individual h there's a number here. But what we want to have that this sequence of numbers for h going to 0 is uniformly bounded. That means, what does that mean if we have this? This gives us, which you should also have heard if you have dealt with numerics of ODEs. There's one that we have now the three magic words of numerics: convergence, consistency, and stability. The most important of the three is stability. And what we have seen here is stability plus consistency gives convergence. And even more, stability plus order of consistency gives order of convergence. We do not lose anything. Because we just, if this thing here is bounded by a constant, we gain the order which we have here. Okay, this is said here, a consistent and stable method is convergent, and the order of convergence is at least, it might be higher, it's not excluded by our proof, is at least as the order of consistency. Okay, so the magic thing here is to prove consistency. Is to prove stability. And that is something which really is a difficult analytical question. And it turns out, and we will later see how we can prove this, that here in our case, for our special 5-point stencil, we can do this quite simply. We can estimate this quantity in the row sum norm by this very nice factor, 1/16 times a squared plus b squared, which is not really obvious. Of course, we cannot compute the inverse matrices in this very special case where we are now, at least in the two-dimensional, possibly also in the one-dimensional situation. There are ways to compute these inverse matrices. In principle, we could do that. This is would be a very brute force method. I'm not so sure about the two-dimensional case, but we will do this all of course, without computing the inverse matrices. Okay, so if we put now everything together, we have our first convergence theorem. It says, and we see all the drawbacks which are also concerned with it. It says if we have a solution of the Poisson equation with a Dirichlet boundary condition on the rectangle omega, and it fulfills that it's 4 times continuously differentiable up to the boundary. This we need to do this order of consistency estimate as we have done it. It doesn't say that for less regularity not a similar result holds true. It only says our technique requires this pretty much unnatural assumption. We apply the 5-point stencil, and then we use the discrete maximum norm, and then the method has order of convergence 2 in the discrete maximum norm more precisely. We can estimate, that's a quite explicit estimate, we can estimate the deviation in the infinity norm, in the maximum norm by, now the factors come in and they multiply up to 1/192. I hope this is correct. It's also not so much important. Times a squared plus b squared. This comes from this term, and the other factor comes from the consistency estimate. In the consistency estimate, we also had these maximum norms of the fourth derivatives. So actually, you see, we need a little bit less than C4. We only need these fourth derivatives, 4 times in x direction, 4 times in y direction. We don't need the mixed derivatives, but it doesn't make too much difference. And now the important thing comes, times h squared. Okay, so what we have to do, and this we will do till the end of the week, we will develop one theory, there are other ones, which allow us to derive stability estimates, like this here. And of course, we should discuss a little bit what we have gained till now and how we can generalize that and what are the limitations in this generalization. Because you have seen already, maybe I'm doing the finite difference method not really justice, but I'm not really advocating the finite difference method. It's just a small warm up before we then start with the finite element method. Okay, let's see. Several remarks, just remarks which I do not prove here for the sake of time. If we look at this estimate here, then we can see we can relax the situation a little bit. For example, if we would only be able to prove that this term here is not bounded by a constant, but it's bounded by c, by a constant over h. Would we then still have a convergence result? And which kind of convergence result would we have? So let's assume we don't have stability in the sense I have defined it, but only we can only prove that these norms of the inverse matrices are not globally bounded, but they behave, let's say, as an example, like C times 1 over H. What does that mean? Plug it all in and put it together. What do we have for the consistency error? What does this mean in the end? So this is the factor 1 here, and for factor 2 is the consistency error here. This one here. And there we had constant times h squared. So what does that mean? Is there convergence or not? Convergence, but only of order 1. So we can relax the result a little bit. We can allow here for negative powers of h, but those, they must be in modulus, they must be smaller than the powers we have in the consistency estimates, and that is the amount what we lose. So that is one point. Two other points, maybe we do this as an exercise. One can say, okay, that was now a nice way to prove convergence with the stability, but maybe we don't need stability. This is wrong, because you can show if you have convergence, then you necessarily also has to have stability, and also if you have convergence, then you necessarily has to have consistency. So that's not only an implication, that is an equivalence. Equivalence is, with the proper notions, convergence is equivalent with stability plus consistency. And maybe a final remark. Let's go back to the definition of the problem. Where was it? Here. What we did here is we have chosen the, so to speak, exact right-hand side, evaluated at the grid points, and used this as, so to speak, the discrete information we put into the scheme. That is reasonable, and also something what we would like to do if the function is smooth enough, but we have a little bit more freedom here. What we could do is we could take here, in this case, any grid function fh, as long as fh converges to f. Of course, always in the same norms we have chosen. If this is the case, we preserve our convergence, and if this convergence has the proper rate, we also preserve our rate. So try to extend the things for this case, substituting the f, which is in notation not dependent of h, but of course also dependent of h we discussed because it's the evaluation of the grid points, but just take any approximation of f with these convergence properties. Okay. Okay, before we now come to this theory, which relates to the fact, whom of you has heard the notion of an inverse monotone matrix? None? That's too bad. It's a very important notion. What the point is will be, what we will figure out that this matrix, and therefore we looked at all these properties. You remember positive on the diagonal, non-negative, non-positive on the off-diagonals with the sums and so on. We will figure out these matrices we're dealing with are inverse monotone matrices. And that is very much related to L-infinity stability. If you want to deal with other norms, with the L2 norm, for example, then other approaches are reasonable. Before doing that, we will first try to see how far can we generalize this, what we have seen now for the Poisson equation and the 5-point stencils. Both are pretty much restricted things. How far can we go, or where are the limitations? So, let's first think about the stencil. So I haven't used very much the stencil notation, but I've switched immediately to the matrix notation because I thought it's more specific. But a little bit more precise would be to write everything in a stencil notation, in the notation of grid functions and, in our case, linear mappings between grid functions. Then we are get rid of this problem of ordering. And let's do this a little bit here. So we define something like the discrete Laplacian, which is just a linear combination of the values of the grid function at the point itself and of all its neighbors in here in general we allow for 9 a 9-point star. So we have north, south, east, west, but also the mixed directions. And we are free to choose these factors. So our old case was only 5 of them, the others were 0, and it was 4 over h squared in the center and the minus 1 over h squared in the main geographic directions. The first question is, can we do better? Maybe there is another stencil which has a higher order of approximation than h squared for the consistency error, and then with the stability, hopefully, for the convergence. We can do this, we can try this, we just do Taylor's expansion in this general case, see how, whether then we get, by the requirements that terms vanish, we get sets of equations for the unknown Cij, and we see whether we can solve them or not. So this is not very difficult to do. And what comes out is the answer is no. We cannot improve this order of consistency h squared. Of course, we could improve it. What could you imagine how to improve it? Is there a possibility to improve that? To get a better approximation for the derivatives than h squared approximation? Let's go a step back. Let's assume we would do that. We would take one of those 9-point stencils. And I will show you in a second one, which is a reasonable stencil. What would that mean for our set of equations? Is it then more difficult to solve this set of equations, or how does it change? Take again the lexicographic ordering, and then we have seen in the lexicographic ordering the matrix has a specific structure, has this banded diagonal structure, and the diagonal blocks are again tridiagonal, and the off-diagonal blocks are just minus the identity matrix. So what we have till now, let's say, block structure, which looks like that. Here we have the diagonal, the tri-diagonal, here the off-diagonal. A little bit too large, this block here. So now, what are the changes if I now do a 9-point stencil instead of this 5-point stencil?
It would be 10.
Huh?
There would be, in 5-point stencil we had
5, and now we have 9, but I want to see where the 9 are. If they would be, say, here, that would be bad, because it would destroy all our structure. We said, okay, the most simple way to solve this is using the banded structure and using Cholesky and things like that. Of course, that would be all destroyed, yeah?
Next to this off-diagonals.
That's right. The only thing what happens is, we get here a further diagonal. This doesn't harm us at all, because it's within the band, and here we enlarge the band by 1. So that's not a big deal. So this we can allow. That would be okay. That would be okay. So maybe at first, before we go on with this question, how we can come to the better order, I show you a good other 5-point stencil. This is one here. So we take, again, we have 1 over h squared, of course. And now we don't have a 4 at the diagonal, but an 8 over 3. And all the others, we have minus 1 over 3. Why is this a reasonable stencil? You get this stencil if you take the 5-point stencil and now you rotate the domain. You rotate x1 and x2. If this is h, what is this then here? If this is h and this is h, what is this? Louder.
Root 2h.
Square root of 2 times h, yes. And if I rotate it, then I get again, so to speak, I look at the stencil now in this direction and in this direction, and I combine those two stencils with certain weights, which I do not know, but are written here. I take this here with the weight, I hope it's not the other way around, 1/3 and 2/3, but the 1/3 is, let's see, maybe it's really like that. So I take this only with 1/3, and I take the other one with 2/3, so to speak, in the rotated, indicated like that, in the rotated situation. And then this is then the step size which I have to apply, because I look like this at the grid. Okay, what is the reason for that? The reason is, if I look at the continuous situation in Laplacian, I can do any rotation, it doesn't change my grid. But of course now in the discrete what I did, I cannot do it, and this is going a little bit more in this direction. That means we do not improve on the accuracy, on the asymptotic accuracy, but we hopefully improve a little bit on the qualitative properties of what we are doing. So that would be one possibility, and we will later on see that we can derive this scheme as most of the finite difference scheme also by a finite element discretization. Now back to the question, what can we do if we want to have more accuracy? What could we do? So we have now said, okay, let's take a general 9-point stencil, not only the 5-point stencil, but a 9-point stencil, or correspondingly then in 2 and 3 dimensions, of course. There's all the corresponding things that we will mention now. What can we do in addition? What choices do we still have? Oh, let's go back to the 5-point stencil. How can we do better with the order, maybe? What would you expect? What we are doing, you have to do the Taylor expansion higher and you have more cancellations, and what does that mean? We have to have a stencil which is more exact for higher order polynomials. How can we do that? Well, we could involve more grid points, for example. And with something like that, we actually can get a higher order. Of course, this has consequences now for the bandwidth. Can we discuss similarly as we did it right now? But what is the real drawback of this here? Let's say, okay, this gives us, I'm not so sure about that, possibly H4, I would guess. If we do the weights correctly, H4 is much, much better than H2. Why don't we do this one? What is the problem? Okay, let's say we look at this point, and now we have to define our domain. Let's first do it like this here. This is our domain. Okay, still everything okay. Now if you discretize here, you see the problem? What is the problem? The boundary. The grid points now move out of the boundary. So the only possibility, so at this grid point I cannot apply this stencil anymore because I get here an artificial point outside the domain. So what I have to do now, at those points close to the boundary, I have again to use, say, the 5-point stencil. And then the question of consistency appears. if I just estimate the order of consistency in the maximum error, then the worst case, of course, dominates everything and I haven't gained anything. It does not say that such a method may have a higher order of consistency in another norm, but these very simple considerations with the maximum norm, which we did up till now, they do not work. Okay. That's basically what is said in these lines. And there is still something what is called the Mehrstellenverfahren, which is in English the Mehrstellenverfahren. There's no other English word for that. I will not discuss this right now. Maybe we make an exercise out of that. Okay, that is the question, how can we go to higher order? Now let's come to this regularity question. One might say, okay, this mathematics has nothing to do with the world, is absolutely unimportant. Who cares that we have assumed that there is the solution C4? It might well be, I said it already, because there are other more better techniques of proof, that those orders of convergence also hold true for much less regularity of the solution. And in fact, with the finite element method, we will be able to prove orders of convergence under much less regularity, and those methods in these very special cases of this orthogonal grids will turn out to be more or less again the finite difference methods. But let's have a look whether this requirement is totally unrealistic. Let's again look at our square. And we have here minus Laplacian. The right-hand side is supposed to be 1. And here at the boundary, always everywhere at the boundary, we take homogeneous Dirichlet conditions. And I ask myself the question, is this solution in, not speaking about C4, is it in C2 up to the boundary? What do you think? Yes or no? Infinitely smooth functions. Constant 1, constant 0. Nothing can go wrong. Or can it? There is some trouble. There is a troublemaker in this problem. Namely, who is the troublemaker? It's not the 1. It's not the 0. It's not the Laplacian. There's not so much left anymore. Where is the troublemaker? Something at the boundary. What at the boundary? That's a very smooth.
Corner points.
The corner points. They are the problem. Yes, exactly. Everything else is okay. So let's look at the corner points. So what happens with the corner points? Having this condition means. So having the second derivative continues up to the boundary also means that the differential equation is valid up to the boundary. So we select a corner point. Which one did I do? It doesn't matter, 0, 0. If I take the solution at 0, 0, then it must, minus the Laplacian must be 1. Okay, so what is this? This is the second derivative in x and the second derivative in y direction. What is the second derivative in x direction in this boundary point? Obviously. 0, because the whole function is 0. What is the second derivative in y direction? So it's a 0. The boundary condition tells me this is 0. So this cannot be. So this is not even in C2. And this is for a very nice domain. This is nice. It has corners, but it's nice because it's a convex domain. And things can get worse if we have re-entrant corners. I've shown you already an example of this type. This is this example. I take the circle. This is my. So I take the circle and I cut out the first quadrant. So this is omega bar, what I've here depicted. So I consider the Laplacian on this. with which right-hand side gets 0. Also a very nice function. And I have some Dirichlet boundary condition here. And of course, these points, there's no problem. The problem comes a little bit here, and in particular here with this re-entrant corner. And we can see this because in this case we can write down explicitly the solution of the problem, because we have a connection between the solution of the Laplace equation and the harmonic function and the analytic functions. And I don't want to point this out too much, so we can just figure out the solution. And the solution of this problem, or one solution, one possible solution, is given in this form here. It's given here in polar coordinates. So x are cosinus of phi, cosine of phi, y are sine of phi. It's given in polar coordinates as the sine term here in the angle, and this term 2/3 in the radius. And you see, and the corresponding boundary conditions are this here. Just evaluate these functions as a boundary. And now we come to these functions because it's the imaginary part of this complex function, and this complex function is an analytical function, and therefore this you can see via the Cauchy-Riemann. Who knows complex analysis, by the way? Function theory? Okay, then at least one knows what I'm going to say in any case. With these arguments you can justify that. It doesn't matter, just to see where the solution comes from. So of course this function we can differentiate, and then you see we get a singularity at 0. And we get the same singularity here in the imaginary part. That means the partial derivatives of this solution blow up if we approach this re-entrant corner. So this solution is not even 1 times continuous differentiable up to the boundary. So we are far away from appropriate requirements. So we need a theory which has less requirements. We will get this with the finite element method. And now let's see what we can do, so to speak, beyond of the rectangular. The rectangle case is of course not very representative. We want to have much more general domains. Sie dürfen gerne den Computer benutzen, aber nicht so. So let's draw a general domain in 2D. Okay, you see all those crosses here? These are already our grid points, so to speak. And now we have a general domain. Doesn't matter. Let's say this one here. Let's first keep it convex. That is not a problem. So, okay. So that is what we want to have, for some reason, our Laplacian. And here we have our Dirichlet boundary condition. So, what is the problem now? What are our grid points? So, we have here nice grid points in the interior. What do we want to... For example, this is a very nice grid point, because here we can really do our 5-point stencil. If you look at this grid point, it's a little bit critical. Because if here we would do our 5-point stencil, we would put this point outside. So, what we have to do is we have, so to speak, to modify our grid. So we have to move this grid point here to the boundary, here by chance we got it correctly. Here we move this grid point here to the boundary. Here we move this to the boundary, this to the boundary, this here. And now we have grid points at the boundary. That is good. Here this is by chance exactly at the boundary and so on. But what now happens? Here everything is okay. Here we have an H, here we have an H. But for example, here we have something like, let's say, what was the notation? I take the same letter. I forgot the name of this Greek letter here, but in any case I take the same one. Somebody remembers how this guy is called? No, it's not a theta. Huh? It's a small theta? Okay, so we have a theta of H, and this is something in the interval 0, 1. So it might well be that at the close to the boundary, we lose our equal stepping of H, and we get a smaller stepping here. So we have to have now other stencils which cope with different step sizes forward and backward and up and down. If we would have appropriate stencils of this type, then everything would stay the same. We would have our stencils here, we would have the values at the boundary points and so on. So let's have a look. So that is the way he's a little bit more explicitly or more precisely described how we define now on the one hand side omega h, and on the other hand side delta omega h. But the problem is now, as I said, we get different step sizes here close to the boundary. Now let's see. So what we would like to do is the following. We want to approximate the second derivative by difference quotients. But we have now the problem that we have an h1 going to the right and an an h2 going to the right and an h1 going to the left. Does this harm us? So we do the same procedure as we did before. The procedure before was we do a one-sided difference quotient on the, so to speak, derivatives, and the derivatives again we substitute again with one-sided difference quotient. That is the formula which then comes out here. Let's first look at this formula. Let's first check whether it's the old one. If we take h1 equals to h2, then we have a 2 which cancels here, then we get our h squared, and you see we have the old thing, we have the minus, the value in the middle, and we have, it's here the derivative, not minus the derivative, and we have minus the step forward and minus the step backward. So we get the old difference quotient back, the old difference approximation back. But what comes out now, the order of consistency, now in our notation that's what it is, it's now not h, or h in the sense of maximum of these two step sizes, not h squared, it's only h. There's a cancellation effect which we had taken advantage of before in the comparison of the Taylor expansions, which we do not have now anymore. Oops, is this here? Okay, so we could do this, but that means in the moment we are close to the boundary, we have a 5-point stencil which only has first order of consistency. The question is, can we do better? Maybe we have just not chosen the correct stencil. And the answer is no. If we just take these 3 values as we did before, so we don't want to have bigger stencils, then there's no choice of those parameters alpha, beta, and gamma, such that we get an h squared order of error here in this approximation. So if we do this, and this is possible, this is then called the Shockley-Weller discretization, then at least theoretically we have the problem that our theory up to now, which only gives us order of convergence 1. In fact, it's not as bad. In fact, also in this case, the order of convergence 2 is conserved, but in other norms, not in the maximum norm. And this requires much more detailed work on the consistency error as we did up till now. Okay. Now let's have a look at at other boundary conditions. In the introduction, I said already the Dirichlet boundary condition, if we do not look at mechanical problems, at displacement problems, is a pretty unnatural boundary condition. Much more natural is a flux boundary condition, which in our special case of the Laplacian just reduces to a Neumann boundary condition. So we prescribe the derivative in the normal direction. So let's describe the derivative in the normal direction. For example, let's first start again with a rectangle. Okay, let's assume that here we have the Neumann boundary condition, the flux boundary condition, which means the derivative in the normal direction is something which is given. So, okay, that is very simple here. What is the normal derivative? How can I write this explicitly here? What is it? Just
W by del.
Yeah, it's just the partial derivative in the x direction, because we are so lucky that our boundaries here are aligned along the axis. So it's just the x derivative. So we need a mean to approximate the x derivative. Here at this, let's say at this, I go a little bit further down, and I have so what can I do? What approximation can I take for the x derivative? We have seen 3. Which of the 3 do you think we can choose? We've seen backward, forward, and central. What can we do? Backward. So we do backward. So we have something like, I use this notation, delta minus h, UH equals G at this point here. Computationally, everything is okay. So we have added a further equation for this unknown value. This value is now not directly given, as in the Dirichlet condition, it's given via this further boundary condition. So it's just an equation. But what is the problem with concerning the consistency, and by this possibly the order of convergence? What is the problem now? This has only order h. So we are again in danger that we lose all the h square conversions. Okay, so let's stick to this for a moment before we discuss how we can do it better. Where is it? It's not at the transparency here, unfortunately. Then I write it down directly. What one can do in this case, one can do it as I described it right now, or one can do it similarly to the Dirichlet boundary condition and do what is called static condensation. One can eliminate this degree of freedom, because that's a very simple equation, this equation which involves this point, because it only involves this point. So I resolve the equation, so to speak, for this point and plug it in the equation for this point here. Then I have done, so to speak, a partial resolution of the set of equations already. And static condensation, just to mention this word, then changes, and that is of importance to understand what is going on. Static condensation then changes the stencil for this point here, for this neighbor point here. Yeah, in which way? Find it again to get the right numbers. Okay. So what happens is, so we have something. We have the stencil in principle now looks like that here, because this neighbor is eliminated. This is similar as to the Dirichlet boundary condition. But in the Dirichlet boundary condition, it was like that. If we did this elimination, let's assume again it was a Dirichlet point. Then we would have a 4 here, a -1, a -1, a -1. So exactly in this case, the entries of the row of the matrix do not add up to 0, but to something positive in the Dirichlet case. Now in this case, and this adding up to something positive, in principle was the reason for getting a matrix which is non-singular. In this case, something different happens, namely we get the weights a 3 here, a -1 here, a -1 here, and a -1 here. That is, now the entries add up to 0. Okay, let's assume we would do that, we would have Dirichlet boundary conditions everywhere. And we would do this similarly, of course, we would then have the other, here we would have the negative x derivative, here we would have the negative y derivative, and here we would have the y derivative, do it exactly the same thing. We get the same stencils. That would mean we would only have rows where all the entries add up to 0. What about the unique solvability of this set of equations? So we have now the problem. We have a set of equations. And I write it in this way. If I multiply with a vector E is the vector which only has entries 1, then I get a 0. That is the property. And then you see already the answer to my question. Is this still regular problem? Yes or no? No. Because we have a non-trivial kernel, of course. Or to say it a little bit more fancy, there is 0 is an eigenvalue of this problem. How is it in the continuous case? What about the uniqueness here? The kernel is one-dimensional, so we can shift the solution just on one vector, by one vector. What is here with the uniqueness of this? Is the solution unique or not? Or what can I add to any solution in this case? Do you see any functional values appearing in the equations, or do you rather see only derivatives? So what can you always add here to any constant? So we have no uniqueness here. This is reflected here. It's not a big problem, but it reflects also the physics which is behind this problem. We said this is just what we have here. Let's compare this a little bit, so to speak. This versus the Laplacian Dirichlet situation. What is the difference? Here we said we prescribed the flux over the boundary. So in particular, we can think of the situation G equals 0. That means no flux over the boundary. In physical terms, this is a closed system. There. Or in the other case, it has a given input in this, just a shifted closed system. What is here? This just says by some magic means we prescribe the temperature or the concentration at the boundary, but it doesn't say anything about the flux which is going on over the boundary. So this is an open system. So what happens now, we said already also, we might imagine these equations as being the limit equations of the corresponding parabolic problems, the time-dependent diffusion problem and the time-dependent heat equation with the corresponding boundary condition, and here correspondingly. What does that mean? Here in the Dirichlet case, because we have an open system, the system totally forgets about the initial state. The initial state doesn't play a role in the solution for long terms, this is only determined by those quantities. But in the closed system, the system has a choice. And the choice is given by the initial data. Because the system conserves something, it just takes the possible solution which has the same conservation property. So the system conserves mass, and so the solution is chosen by this possibility to shift by the constant, which has the same mass as the initial data, in the case of g equals 0. Okay. Of course, yeah. Now, two things. The first thing is we have to do this better. How can we do it better? What is better than the one-sided difference quotient? What do we do here? No, here. Not the one-sided, but what?
Central.
The central. But what is the problem with the central?
We don't have a value on the other side.
Now we get this ghost point into play. Can we cope with this ghost point? Yes, we can. Okay, we have now an equation. What do we have to do is we have to need additional equation also involving this point to get a chance to eliminate this point in the sense of the static condensation. So what do we do? Where do we get a further equation which involves this point? What do we have to assume? Or what do we have to do? How do we get a stencil which also involves this point? What about, I don't have color. What do I have? No, this was too much. This was too much. I do it like that. What about this here? So what do? I assume that the differential equation is valid up to the boundary. Might be or might be not. In this case, it's reasonable. And I do the same discretization here. I get an equation which involves also this point, but this I can eliminate this unknown or also leave it in the problem and then throw it away. And if I do that and do the same elimination of this point here again, I get a stencil. Now this stencil here, and the weights of this stencil are now 4, -1, -1, -2. You see again, it adds up to 0. So when we said, so we are in this notion close to the boundary, we have to change this close to the Dirichlet boundary. So we need a bit of a Dirichlet boundary in the problem to assure the uniqueness of the solution. Okay, the next thing I skip maybe, and let's start. The last 5 minutes we have. We start with the way to prove stability of the scheme. It has to do with the so-called maximum principle. So we're dealing here with the Poisson equation, and this type of elliptic equations, they fulfill a maximum principle. This exists in different forms, I just stated here. And we maybe we do something in the exercises or concerning the proofs. And what we will then do, we will try to mimic, to find this again in the discretization. So we will try to formulate requirements of the discretization such that also our discretization fulfills a maximum principle. And this maximum principle, as we will see, is closely related to what is also called a comparison principle, and in the end to the stability with respect to the infinity norm. So what is the maximum principle for the Poisson equation? So we have to have a right-hand side which is less or equal to 0, so we have a sink and not a source. And then this, so in shorthand, f less or equal to 0. And then the statement of the maximum principle is that the maximum of the solution on the closure of the domain on omega bar is less or equal the maximum at the boundary. So it's not possible that in the interior, in omega, a larger value is attained as at the boundary. That is the statement. That is the weak maximum principle. Of course, if we multiply everything with minus and we get f greater or equal to 0, then we get a weak minimum principle. It's therefore I only state the maximum principle versions. Okay, so this holds true also for more general equations, so it need not to be the Laplacian, it can be a general operator with such a matrix called K coming up in this second order operator. And we can also have a part with first order derivatives, a convective part that also does not harm the validity of the maximum principle. What is a bit of a problem are those terms which only depend on u without derivatives, which I would like to call reactive terms, because there's something in the most simple case, something like exponential decay, what is written down here. If you have an equation of this type, then only a weak form, modified form of the weak maximum principle holds true, namely we can only estimate the maximum on the closure by the maximum on the boundary and 0. That means if we get a negative value here, we only can estimate by 0 the solution, not by this negative value. Okay, then there's also the strong maximum principle, which basically says if the maximum, so what at the moment with the weak maximum principle is still possible, it's possible that the maximum is attained in the interior in omega, but the only thing what we know, it also has to be attained at the boundary. The strong maximum principle says the only possibility for this case I just described is that the solution is constant. So the strong maximum principle says if the solution has a maximum in the interior, it must be constant. Then of course it also has its maximum at the boundary. And the same result we find again now for our 5-point star discretization. And this said, so we consider the 5-point star discretization, we assume that this solution attains its maximum at this set, so these are the grid points in the interior, and this is delta omega h star. This is nearly the boundary of the whole thing. That's the boundary of the grid up to the 4 corners. Then you might have noticed or not that the 4 corners, they do not appear in any stencil. You think if you take the stencil here, this point never appears here. So of course it can have no influence on the solution. So that's quite natural to do it like that. And the assertion is then exactly what I stated concerning the strong maximum principle. In this situation, the solution is constant. If it attains its maximum in this domain, then the solution is this is a misprint here. If the solution attains its maximum, this is a misprint here. A very strange misprint. Hopefully it's corrected here. It's not corrected here. Okay. The correct version is that the solution attains its maximum omega h in the interior, then it must be constant on the whole domain with the boundary in this sense. The whole domain with the boundary a part of those 4 points which do not play any role. And of course, as a consequence, of course, the maximum then on the domain, under the grid points, is less or equal than the maximum at the over the grid points at the boundary. Okay, this we will show next time, and then we'll see how this is related to matrix properties and how we can generalize.